Okay, just a quick comment. If RT is this, which is a typical expression for a projectile, it does not follow from this that RT equals this. You can't add this and even throw away the I and the J. These don't commingle. They don't. You got a component this way, a component this way. You don't just add them head to tail. You add them as vectors, right? So doing this would be like just adding them head to tail. Okay. So that just, you don't do it. The other thing that these two expressions have in common, incidentally, and this is an important principle, so make sure you pick it up. The only thing that these two have in common is time. Okay? All the other quantities you see on this slide have no effect on one another. X coordinate has no effect on y coordinate, y coordinate has no effect on x coordinate, which is another way of saying you can't just add these things without the i's and the j's, okay? Okay, so now a couple other things that came up when we're trying to do what we're trying to do today is in asking a question about the kinetic energy of a magnet on a beam as it's rotating around. Nobody could tell me the definition of kinetic energy. Okay? Yeah. Some said something about angular velocity and stuff, and they're kind of in the right idea, the right conceptual constellation. Okay? So that's not terrible, except that we just did this and you've solved problems with it, and you'd solve the problems right, but that apparently the definition of kinetic energy ever sinking in, or the fact that it even has one. If it's just symbols on a piece of paper that you plug numbers into, it doesn't have a conceptual presence. Okay? You want to develop that. And to develop that, I think it's important to be able to go back to basic principles. Okay? So, basic principles, and this is the way I presented it in the first place. And of course, this last class, I presented impulse momentum in the same way, and we hopefully have connected that with this in the way it's derived. And just deriving it for a constant net force, okay? Much less integrating and stuff, which isn't any harder. We made an assumption. What's the basic assumption? Okay, well, first of all, work energy comes from considering net force acting through displacement. Impulse momentum from considering a net force acting over time interval. Okay? What do? Assuming a constant mass, you get a constant acceleration from a constant net force. Okay? And if that force acts over a displacement, what effect does that have on anything? Well, right here is one of the equations of uniformly accelerated motion that again comes from first principles. Okay, definition of acceleration, definition of velocity, either through the calculus derivation or through a derivation. One you should know. Okay? So, and then this actually comes from two easily derived equations, one being this one that we use for momentum, and the other being easily derived, just involving average velocity. Okay? And you combine those and you eliminate t and you get this equation. Okay? And you need to be able to do that. I want you to understand where everything comes from. I want you to have it there from first principles so you don't have to rely on memory. Okay. Now you're probably going to remember, but if you didn't, you easily rederive these things. Okay, so anyhow, yeah, so we take that acceleration, plug it into here, it gives us our definition of working kinetic energy. I'm not going to do the details. Okay? I've already been done. And just last time I did the details of this one. When we plug the same thing into this equation, because it involves time instead of displacement, and you get your definition of impulse and momentum. And there they are. Kinetic energy is 1/2 mv squared, momentum's mv. those are not just formulas that you memorize. They have a meaning that comes out of understanding what's going on here. Okay, there's a reason this has the 1/2. Okay, could also be done with calculus, and 1/2 comes from integrating velocity with respect to velocity. Okay, but you want to understand this, so you don't leave the 1/2 out of the kinetic energy formula. It's not just a formula, it's a concept. It's a concept that's totally related to the idea of work. Okay? Right there's your basic situation. Here's what follows from it. Okay. And then, in addition, we just spent time talking about the definition of a radian, which nobody remembered. Okay? And how we use that with the mass rotating on the beam in circular motion. Okay? Where we can easily estimate or measure the angular velocity, and where we assume we know the mass. Okay? We have to know what a radian is to be able to reason that out, unless we want to use a formula we don't really understand. Okay? The formula is great if you understand it. You don't understand the formula if you don't understand what a radian is. Okay, so anyhow, this leads into the thing I wanted to talk about. Okay? We're going to have less time to talk about it, but we'll make these connections. Hopefully, it'll make a lot more sense if we hadn't had this discussion. Okay?
We need plenty of review.